All right, welcome everybody. Let's get started with our today's lecture on game AI. And sort of as always, we will briefly recap what we did last time, and then we'll take a step back and then descend down another path of computational intelligence. So what have we been studying the last couple of lectures? We've basically been looking into the problem of behavior programming. And, first of all, we saw that behavior can be something rather complex, something that may involve a lot of contextual knowledge, something that may involve a lot of world knowledge. And we had this hierarchy of behaviors. And we saw that on the sort of lowest level on this hierarchy are simple reactive behaviors, things we do that do not require lots of thought, that do not require lots of planning. And accordingly, if we want to implement behaviors, it appears, and of course that's right, that these simple reactive behaviors are the ones that we can implement in a rather straightforward manner. If we want to implement tactical behaviors or even strategic behaviors, there is much more effort involved. We have to do planning, reasoning, stuff like that. For these reactive behaviors, there are numerous very simple computational models, and those are the ones we are studying right now. In particular, we have been looking at the idea of finite state machines or finite automata, and sort of slightly generalized it towards the idea of transducers, which basically are state machines that also generate an output. And the last two lectures, where we looked into what is it to say that something is a finite state machine, what defines a finite state machine. We can do that very rigorously in a very mathematical manner, which is great because that allows us to prove things about their behavior, about their capabilities, about their features. In particular, we looked into the problem of simplifying these finite state machines. And actually there are theorems about when a finite state machine can be simplified, that is reduced to a finite state machine of fewer states. Are there superfluous states in there? We also looked sort of at the, ever so briefly, at the opposite end of things. That was the idea of composing finite state machines or transducer into more complex models. And looking at all of this, it appears, first of all, that they are rather simple things, conceptually simple things. Everybody, you can tell your grandmother about a finite state machine, just draw a diagram and say there is a state here, and if this happens, we go to this state, and you draw the diagram. Everybody will understand that. It's very easy, conceptually very simple idea. It does not really require a deep background in computer science to design a finite state machine where we would say, okay, this is a plausible model of some behavior, say, of some game agent. So conceptually easy. There are strong mathematical results about their nature, how they behave. We can simplify them, we can compose them. In particular, in combination with scripts, finite state machines are therefore very, very popular in the gaming industry when it comes to programming NPC behavior. And these are things that are known, I don't know, the idea of at least 80 years, I would say, and went through a boom period after Chomsky sort of invented this field of computational linguistics, and then these results on simplification and composition are all from the 70s. So these things are extremely well understood and established in computer science. And they're not, because they are so well understood, there's not much research going on in this area anymore. For some reason, it's hardly ever hear about them in a modern curriculum. But they are still the state of the art, sort of in the gaming industry. Now, let us take a step back. Right? Let us take a step back and have another look at what we actually did there when we talked about this idea of state machines. Right? In particular, isn't it true that a finite state machine is just a set of if-then rules? Sure. Right. Finite state machines are nothing but if-then rules. Let me make that explicit. Let me make that explicit. And of course there will, certain things are best explained in terms of an example. In particular, given the kind of state machines we have been looking at during the last couple of lectures, let's sort of remember one of those. We had this application example of an NPC that's supposed to guard a treasure. And we had a couple of states in this state machine. One of the states was called guard. So we could say if a state, this is now a variable s, is guard, that was one component of these if-then rules we are going to devise right now. And now it becomes clear, the health of this character that is supposed to be guarding a treasure is greater or equal than, say, some 20%, whatever that means, we don't care. And yeah, there is another, oh wait, don't make it slightly more abstract. The 20% were from last time, but today we talk about abstract things. So if the health is larger than some threshold theta, say, so this is another Greek letter theta. So if that character is in a state that is called guard and its health is larger than some threshold theta, and how do I write this? The distance to an enemy, well, this is yet another sort of variable, something that we can read from the attributes of the current game state. Say if this distance were less than some threshold delta, well then what this finite state machine did, we discussed last time, was that it would transit to a new state that was called charge. Yeah, I have another rule here, but why write it even down? Why bother? Everything we need to know is apparent from this example. So in a finite state machine, we had these states, we had these input symbols, and we said that given that we are, as the character, in a current state and observe a certain event in the environment, for instance, that our health is larger than some threshold and our distance to an enemy is less than some threshold, then we would have to transit to a new state. That's it. Finite state machines are a fancy way of writing down lots of these if-then rules. Right? In particular, there's sort of a graphical representation of many of these if-then rules. Yeah, and then we can now ask a question. Do we actually need these states? Do we need these states? So, do we need states? And the answer is probably not, or maybe not, probably not. We can sort of simplify this rule I just erased like this. Here is the simplified example, we could basically say if the health of that NPC is less than some threshold and its distance to an enemy is, I don't know, less than, here we had larger, have to be consistent, so that was larger, and here we have less than some threshold. Well, then I probably don't have to actually transit to a state that would tell the NPC to charge. We could simply activate the script for charging, right? So this is different from what we have done so far. So far, we understood the NPC to be in a certain internal state, and there were not so many of them. Typically, there can be a lot. And we defined a couple of rules for how to transit between these states. And with each of these states, we associate a certain script that would render a graphical output, or, I don't know, update game variables such that, I don't know, whenever you hit your opponent with a sword, then the health of the opponent gets lowered. When you're being hit, then your health decreases, whatever. So far, we said we are in a state, and if something happens, we have to transit to another state, and there we do something appropriate. But we can do something appropriate without being in a state. Yeah, you have a question?
But doesn't that get so much messy when the cases are more and the input variables are more?
Yes, yeah. So her question was, doesn't that get messy? Yes, it does. In particular, the beauty about tying these things to states is indeed that we can argue about that using these formalisms we have looked into last time. Here, it is probably not as guaranteed that we will be that there will be no conflicts in, like, I don't know, thousands of these rules. Some of them may contradict. We cannot. I mean, it can be determined automatically, but it's not as elegantly, right? But still, why shouldn't we? Why would we need states? We can, think of statelessness. And indeed, this is, again, just simple reactive behavior. So the AI routine of the game is called. First, it's established, like, what are the current values of these attributes, and then depending on these attributes, we do something, regardless of what we have done earlier. And so this is even more reactive than the state machines we have been looking into so far. And of course, I'm doing this with a purpose, right? It's not that we could have started with sort of this simpler setting and then extended it to state-based transitions. But we, in a sense, have started with a more complex setting. And now we are actually simplifying what we did last time. Now, we don't need states anymore, but still we are dealing with lots of if-then rules, clauses. And these clauses involve tests on the values of game attributes, game entity attributes, health, distance, stuff like that, can be computed from the current instantiation of the game rule, from the current game state. We can compute these values and then we can check them against thresholds. Right? But where do they come from? How to set these thresholds? Which one did we have so far? Such as theta or delta. Where do they come from? How do we set them? Yeah, as always, the answer is, like, whenever, like in computer science, let me not for computer science, let me talk about artificial intelligence, pattern recognition, machine learning, these kind of things. whenever we encounter thresholds in this larger area of artificial intelligence, where do they come from? Right. Mostly they come from experience or intuition. Of course, you can run, I don't know, lots of simulations of the game, gather statistics, and then based on these statistics, apply machine learning techniques, statistical inference to sort of come up with suitable values of these thresholds. Nah, but that is really cumbersome. In particular, if we are dealing with more than 2 thresholds, like say in order of thousands, that is hardly actually ever possible. So where do they come from? Well, some designer, some programmer sat down and said, well, it works best when I set theta to 20%. Now, why not 19.8? Who knows? Right? 20% is, these rules of thumb, and they come from intuition. Yeah. Now, but then we can ask, intuition, is that intuitive to talk about thresholds? I don't know. When I'm talking about, say, weather today, I'd say is a rather warm day. It's not a day with a degree less than 30, but higher than 20 degrees. But this is, we don't do that, right? This is something we don't do in everyday life, and still when we write programs, we do it all the time. The question could be, couldn't we try to use our everyday reasoning, say this is a warm day because it is rather sunny and there's a slight breeze in the air. Right? So what does it mean to be warm? What is the difference between warm and hot? What is rather sunny and a slight breeze? We do not make that precise when we talk about this. I never say, well, today it's more than 22 degrees, but less than 27. I say it's a rather warm day. So therefore, wouldn't it be even better to consider rules like and I'm just again updating the if-then rule we have been looking at so far. So we could say if health, what do I have here, is low, and say enemy is near, then there's a different rule actually than the one we had so far, then flee. This is again something you could possibly explain to your grandmother. And even though she may not have any background in computer science, this idea of checking thresholds is rather abstract. But if we were to say, well, let's try to formalize or implement this issue of behavior programming in terms of rules like this, well then at least from the point of view of the game designers, this is again very intuitive. Because this is now using if-then clauses in terms of sort of everyday concepts. This somehow apparently mimics the way we reason in our everyday lives. To us as cognitive beings, it's sort of sufficient to say something is rather small, low, something is rather close, near, whatever. And we do not have to have a precise measurement which we then can threshold. Right? Now, and that is what we are going to look into today. namely the question of how to compute with these kind of concepts. Like, what does it mean to be low, near, or whatever. And this is going to be fun, because this is indeed rather straightforward. So today we'll be talking about fuzzy logic, or let me say a control, fuzzy logic and control. First about logic, then about control. Probably should say this goes back to work by a guy called Zade, I guess it was in 1965, is a beautiful example for the value of showing tenacity. I forgot how his original paper on this topic was called, but if I remember correctly, he's been trying to publish that for 15 years or so. So he had developed this theory of fuzzy logic and control, wrote a paper about it and got rejected for 15 years. And then eventually it was published in a journal where the editor was a friend of his. And so, yeah, come on, it has been rejected so many, I'll just print it anyway. It turns out it's one of the most cited papers of all times in computer science, like more than 100,000 citations. This is of extreme practical importance, and has, I don't know, I'm not a fuzzy control researcher, so to me it's fun, but there are people that who take it tremendously seriously and dedicate their whole life to researching the ideas we'll be studying today. So yeah, if you get rejected, keep on resubmitting. Maybe you'll make it big eventually. So before we do that, I will introduce two terms that are frequently used in this context. We would not have to do that because, as we will see, this is just renaming things we are using anyway. The first term is the idea of a linguistic variable, and that is supposed to refer to a variable x, let me call it capital X, a variable capital X, whose, and I'll put it, this is my own, whose possible values are words, or terms, sentences, I don't know. Terms, let's say terms, because then we can immediately introduce the second one. A linguistic term is used to express the value of such a linguistic variable, so it's a value of a linguistic variable. And I know that these definitions are rather dry and abstract, but let's look into an example and it will become clear instantaneously. So, for instance, let us think about the variable x, and let us assign a different name to this variable, say health. Right? Now, we have a variable health, a linguistic variable, and we say its possible values are words or linguistic terms. So health can have a value in this set of terms, say low, medium, high, I don't know, make it very high, and ultra high. Whatever that means will become apparent in a second, but you know, if we are talking about health, then we say, oh, he or she is in good shape or in good health, or health is really going down. But we say, how do we measure health? Right? like for human beings. We don't, but we say good health, bad health, something like that. So health is a perfect example for something we can talk about, and we do it every day. And if we are talking about this, we are talking about this in terms of linguistic terms. And hardly ever in terms, oh, his health is 8.7. What does that even mean? And that's that. So this is at the heart of fuzzy logic that we are now trying to develop a formalism for how to compute with these things, how to do that on a computer. And probably I should not have talked about everyday health because I have to get that out of your brains right now. Because whenever we are doing something on a computer, in the end, at the very bottom of it, it is manipulating numbers, right? Or strings of zeros and ones. And these numbers can represent character strings or indeed measurements. And for instance, in the context of computer games, of course, there is a number attached to health. Right? If you're a non-player character, you have a certain health value, which we can measure, which is an attribute of the NPC. So in the context of games, we can measure these things. But even if we can measure them, we hardly argue about these things in terms of numbers. So our question now is how to, even if we can measure them, first of all, assign these measurements to these fuzzy concepts, and then how to compute these fuzzy concepts. Right? So we have two questions. The first one is how to compute with linguistic variables, and the second one is in the context of computer games. And I'll have to get rid of this health example from everyday life. Let's think of the health example in the context of computer games. So things we measure are, say, crisp. Right? A computer game character has a health of 57 at some point throughout the game. This is a number. We could add and subtract stuff from that number. So in the context of simulated worlds, such as computer games, these things are not so fuzzy but crisp. And that's okay, but we want to try to use our fuzzy reasoning to talk about these crisp things and to derive rules that guide behavior from these fuzzy concepts. Are crisp and not fuzzy. And not fuzzy. And so therefore we have to ask the question, this is the second one, how to fuzzify crisp measurements. That should actually be the first question we answer, because once we have fuzzified the crisp measurement, we can then address the question of how to actually compute with this fuzzified variable. And now, without further ado, all of this is beautiful because there is a very strong theory underlying all of it. Again, we could write down definitions and begin to prove theorems given our actions here. But the beauty is that it becomes immediately clear if we just look at a couple of examples. So today we will really be learning in an example-based manner. Let us first study the behavior of crisp sets, or the characteristics of crisp sets. And our example will be, what do I have here? A variable called health. So this is our linguistic variable, the one that we'll use to develop all of this by means of examples. And as I am lazy, instead of health, I will call it capital H from now on. And as I used to play it quite a lot, I know a lot of health in a game called Quake 3. In Quake 3, because there this variable health can assume values between 0 and typically 100, but there are so-called power-ups, so it can actually go up to 200. So again, in a real world computer game, health is something that has a numerical value, right? And in this particular game, it is something between 0 and 200. And so therefore it can, be something that is in the range, in the interval from 0 to 25. And now again, experience or intuition would tell us that this is a rather low value of the health variable. It could probably also be, and can definitely be, in the interval between 25 and 75. Then we would call it maybe medium health, and everything between 75 and 100 would be high. And now I'm just making things up. Everything between 100 and 150 is very high, and everything higher than 150, so between 150 and 200, is ultra high. Ultra high. Right. Of course, how did I come up with these boundaries of the intervals? Intuition. It does not really matter, and we will get rid of them very soon. But we see that our question right now is, how can we fuzzify crisp measurements? And apparently, a linguistic term in the context we are studying right now is an interval. Right? The linguistic variable itself is a number that can assume values in a certain larger interval. Let's call it a set. Right? And the linguistic terms refer to subsets. The subset of health values between 0 and 25 would be representing our concept of low health. So therefore, we can, just from looking at this, deduce that linguistic terms can be thought of if we are going to think about things, how to implement this on computing machines. We can say that linguistic terms are sets. So for instance, this term low with respect to the variable health, I'm indicating that by this subscript here, is the set of all values h in capital H, such that, say, 0 is less than h, which is less than 25. Right? I'm indicating the linguistic variable when I'm talking about the linguistic term low, because other things can be low as well. Right? In this example of the shooter game Quake 3, you have also some sort of armament, and that can be high or low. And in order to point out about what linguistic variable we are talking, I am using these subscripts here. Right? Because we could also have low armament. We could use different linguistic terms there, like insufficient armament or whatever, but maybe we want to call it low, and so we have to distinguish the low we are talking about. This is the low with respect to health. Okay, it's great. Now that we have agreed on, I hope we do, the idea of understanding linguistic terms as sets, we can have another look at this. And that takes us back to something that has popped up a couple of times throughout this lecture already, namely the idea of indicator functions. Right? So let's look at the indicator function point of view on this. Indicator function point of view. Why not define a function, let's call this mu, and again I am using this Greek letter because everybody does. So in the literature on fuzzy logic, typically you'll find the character mu at this point. And this is supposed to be a function that represents this set of low with respect to health. All right? It has two subscripts because we will have lots of these functions, and these functions will indicate these sets, and of course we have to make sure that we know what kind of variable we're talking about. Right? And the function is being applied to a health measurement that we probably can read off the current game attributes. Right? The game state says this character has a health of 75. So this h would be 75. Now we ask for the values of this function, mu. And it's an indicator function, so basically we define it like this. This function mu low h of h is 1 if this variable h is in this set, right? And 0 otherwise. Yeah. We should be used to that by now. The question is, why? Why would we, you know, this we perfectly understand this. Why do we have to think about this in terms of functions now? But these two things are of course equivalent, right? There's no question. So let me illustrate what we just did. Again, we have the linguistic variable health. It can assume values between 0 and 200, say. And now we define a function mu low, and obviously the domain of that function is all the values of the variable health. But we say mu low h of h is 1 if the value h is in this set. But this is basically to say, so here is 25. So this function looks like this. It's a rectangle impulse. It's a rectangle function like so. Right? Here is 1. And for every other value, it is 0. It's a perfectly valid definition of a function. So this one would be mu low h of h. Right? I haven't defined it, but let's assume we would have defined another function, another set for, I don't know, let's say the high health values. So we have, well, I did it when I wrote down all these intervals here. So there we had 75 to 100. A function that looks like this, like so, would actually indicate is the indicator function for what we called the set high with respect to health of h. Right? So yeah, this is, and I'm doing this just to have a different approach for computing with sets, right? Because once again, so this is why we're doing this. I note that it is equivalent to say that h is in the set low h, low subscript h. This is equivalent to saying that mu low h of h is 1. These two things, of course, it was defined like that. And then therefore this is equivalent. And of course, if it is not in this set, then this would be 0. So it's okay. We can do this. It doesn't matter if we are talking about, if we're trying to check set inclusion or evaluate a function. Now, therefore, we can restate these if-then rules that sort of stood at the beginning of all of our discussion so far. Because of this equivalency, we can write this rule if h is low and enemy is near, then flee, can be written, or let's say recast as the following if-then rule. If, let me see, yeah, mu low h of h, and this one is mu near of a variable d, which indicates distance, right? And it has a current value of d, then flee. So once again, when we talk about designing rules in order to realize behavior, it may be that for us as human beings, it is very intuitive to think about these rules in terms of these linguistic terms, right? If health is low and enemy is near, then do something. And this is great because whenever we do that, we don't really have to fix a certain number in our minds, but there is always this sort of concept of what it means to be low or near or whatever. And well, asking if health is low is basically asking if h is in a set, in a certain set. And now we have said that, well, instead of sets, we can as well talk about functions like this. Right? We can, instead of defining these sets, we can design lots of functions like this. And then we could express this if-then rule in terms of these functions. Basically, we could ask if mu low h of current health value and mu near d of current distance value. This is either something that is 0 or 1. This is something that is 0 or 1. So we can sort of Boolean end them. Right? This is just Boolean values if we want. If both of them are 1, then do something appropriate. Right? And once again, when I defined these indicator functions, I did so with respect to these sets. Right? But I could have done it the other way around. I could have drawn a function like this and then defined the set. So they are really equivalent and it doesn't matter which one we do first. I draw some rectangle function and then some rectangle function, like very good health, say, I don't know, would define a set. Or I define a set and then immediately defines a rectangle function. So they are really equivalent. And we can compute with these because now, however we define these rectangle functions, we measure some health value, say this one, evaluate the function, find, oh, here it evaluates to 1. Like the high function would evaluate to 1, whereas the low function would evaluate to 0. So can do that. Right? And that answers our second question, because these functions are a way of turning crisp measurements into fuzzy terms. Right? Because every measurement between 0 and 25 would be turned into something we'd call low. Right? And as we have defined that as a function, now we can actually really immediately compute the fuzzy value of a health of 90. Yeah, but where is, you have to raise concern now. Some concern. If we are honest, isn't that exactly the same as defining thresholds? Yeah. Here? Yes, it is, right? So far we haven't gained a lot. Because we say, okay, let's get rid of these threshold things, and cleverly disguised, we did so, right? We talked about, I don't know, linguistic terms, low, medium, high, whatever, and then how to map numbers to these terms. And when we are mapping numbers to these terms, we probably immediately need thresholds again. And this is something we did want to avoid. So, can we get rid of this? Can we sort of try to extend this idea to something where we would say, okay, this is indeed even more appropriate with respect to our everyday experience. In particular, why should it be that a health value of 24 is low, but a health value of 26 is not anymore? Right. Why is it that I don't know, something that 22 degrees is warm, but 23 degrees is hot? Which is probably not. These crisp thresholds are really rather counterintuitive. And the question is, can we turn this into something that is even more appropriate to the way we would reason about the world? Well, we have already found a way of sort of turning numbers into concepts such as low, medium, and high. And by introducing these indicator functions, we can now actually do a computation with these terms, low, medium, high, because in the end they are just values between 0 and 1, whatever. Now the question is, can we extend that further? And this is where this idea of fuzzy sets comes in. And typically, if you read the literature, you will not find this. But we could do it because we've been talking about indicator functions earlier. And since we have been talking about indicator functions earlier, we can now indeed immediately understand where this fuzzy set idea comes from. And this is a generalization step. It's basically from crisp, let's argue just about indicator functions. So what we are doing now is we generalize from indicator functions, which are functions mu of some value x that assume two possible output values. So they have a certain range, a certain domain, but the range is discrete. They are either 0 or 1, right? They are these rectangle functions so far. And we extend that to membership functions. Membership functions. And they are also called mu. This is a different mu now, and we'll see in a second, because here we assume that these functions can take any value between 0 and 1. Note the difference of the brackets here. Here we have curly brackets, it's a set. Here we have square brackets, it's an interval. These indicator functions assume a value of 0 or 1, and these membership functions assume values between 0. Can be 0.78. Could be a value of a membership function. Again, this is immediately explained in terms of an example. And we stick with our health example. All right, and let me see. That's 25. What do I need? 75, 100, 150, and say 200. So this is the range of possible health values when measured from within the game world. And now we could say, well, low health is something like this. If it is a number between, say, 0 and 10, it is definitely low. But if it's a number between 10 and whatever, 50, then, I don't know, 25 is not that low a health, and 50 is probably like definitely not a low health anymore. And we could say, so this would be low, and this would be medium. Medium, what do I have for high? Yeah, something like this. This is again just a contrived example. By no means do these triangles and trapezoids represent like ultimate truth. So this is very high, and this here is ultra high. Ultra high. Maybe you have seen these before, have you? You have a question?
Why triangles without Gaussians?
Nobody knows. So her question was why triangles and trapezoids? Indeed, this is an extremely valid question, and as always, there is no answer to it. Yeah, we could instead have used Gaussians, say, and why not? Or we could have used any other function that has this characteristic, right? Like that is defined over a certain domain, and over this domain it assumes values between 0 and 1. Why triangles and trapezoids? It's very convenient. It's very convenient. Right? But again, we could have also used, I don't know, membership functions that look like this. I don't know, make it. This has to go up to 1. But does not have to be piecewise linear. But the fact that you know we can as well choose them to be piecewise linear is like very convenient for implementation. It's very easy to represent these kind of functions in a computer, if you think of it. The take-home message is that by instead of using indicator functions, going to membership functions, we have now introduced uncertainty into our domain here, right? Because, for instance, something, if we measure a health value of 30 for the game character in the current situation, in the current game state, then this value of 30, make it 35, something like here, it does have a membership value with respect to the set low that is larger than 0. So let's say we observe whatever, let's call this number, I call it 40, right? So a health value of 40 does have a low membership of, I don't know, what is this here, 0.1. I'm making this up, right? Does have a low membership of 0.1 and a medium membership of, whatever, 0.5. That is to say, this observation of a health value of 40 it can be both. It can be low health and it can be medium health. And given the way we have defined it, is more likely or rather medium health than low health, but still it can be both. Right? And this is great because we still have to worry about how to define it. I have used a couple of them here, how to define these shapes, and this again requires experience or intuition or whatever knowledge about the problem we are dealing with. But if we have defined them, and if we define them, we still need this threshold thing. But decisions we can base upon this are not dependent on certain fixed thresholds. But now something can be either low health or medium health somehow at the same time. And this is good if we could devise a way of reasoning with this, then it would be less dependent on setting the right thresholds. Right? And this is, again, just an extension of these indicator functions we have been talking about a couple of times throughout this lecture already. Indicator functions indicate set membership, and now we have extended them to membership functions, and they indicate degrees of membership. Right? You can be of a tall height or a very tall height, probably at the same time. What distinguishes tall from very tall? Right? People that are 240 meters are definitely very tall, but what about 192? This is definitely tall, no question about. Maybe it's already very tall. Who knows? Like, how would we draw the line between tall and very tall? If we agree on this idea that you can be both, then we gain flexibility. So again, this health value of 40 can indicate both low health and medium health. And in this example, it indicates rather medium than low health, but it doesn't matter. Now, this raises a crucial question, because so far we have been dealing with a situation where the indicator function had a value of 0 and 1, and now we are talking about situations where we have membership functions with values between 0 and 1. Can be 0, can be 1, but can be anything in between. If it is 0 or 1, we can do Boolean logic or these kind of things we need for if-then clauses, right? But what does it mean to say 0.2 and 0.4? How do we do ands and ors and nots with these membership values? So the question is how to do, I don't know, make it logical operations with membership values. Is that even possible? Is that even possible? And it turns out it's no problem at all. We just have to take another step back and look at what we know about operations, Boolean operations such as and or, from a different perspective. So therefore, let's ever so briefly look at the basic operations of Boolean logic and how we typically do that. So we have two variables a, and we want to AND them, b, a and b. We look at these tables, a, b, so make it c is supposed to be the outcome of a and b. And here we have c. And we know these kind of terms. So we have 0, 0, 0, 1, 1, 0, 1, 1. Given two Boolean variables, those are all possible instantiations of these variables. We know that 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, but 1 and 1 is 1. That's cool. We look at C is A or B. Don't really need that for our if-then rules so far, but let's still look at it to see that what we are going to do is indeed very interesting. 0, 1, 1, 0, 1, 1. not and not is not, or not is not, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1, and then let's, I don't know, make this B is not A. So here we have A and B, basically just two of them. Oh, that's it. Right. These are the elementary operations of Boolean algebra. We can derive more complex ones, such as XOR or whatever can be derived therefrom. And this is the view we are used to. Now, I'll just throw one in front of you, and then you tell me the others. If we look at this table that defines what we understand under the operation AND of two Boolean variables. And usually we understand them to be, you know, false or true, 0 is false, 1 is true. And this is a table that would define that. Once we have defined, like we can develop the whole area of logic from these actions here. If we understand them as numbers, which we also do quite often, indeed 0 and 1, consider this. A and B, C equals A and B, is the same as C is the minimum of A and B. Quickly verify that. Is it true what I just claimed? Right. We have 0, 0, minimum 0. 0 and 1, minimum is 0. 1 and 0, minimum is 0. 1 and 1, minimum is 1. Oh boy. Interesting, eh? Now, then, what would I have to do here? Or is max. Indeed. Max of A and B. And not? 1 minus. Exactly. So this is 1 minus A. Have you ever thought of this? Right, if not, no, you know it. It's great. Indeed, we can do. We can understand these Boolean functions as sort of algebraic functions. They are not, but as operations with real numbers. And this then, of course, would allow us to define what is the meaning of 0.2 and 0.7. Just the minimum, right? Just the minimum. There you go. There you go. So these membership values can be ANDed if we understand ANDing as taking the minimum. And why shouldn't we? There you go. Okay. So that answers our question how to define these operations of AND of two membership values. We just take the minimum. Okay, then ever so quickly, how do we do that? How do we, now that we know that we can fuzzify measurements and that we can do Boolean, well, you know, fuzzy logic operations with them. How would we use that for inference? That's quite easy, and this is so straightforward. We just do that by means of examples. So, fuzzy inference, and without further ado, here's an example. I'll define, I don't know, two variables that are of interest for us in game AI: health and distance to opponent, right? And then we somehow have introduced these fuzzy sets, and we can say if health is low and the distance to the opponent is close. You see, I'm just using a different linguistic term. It doesn't matter. It's your you know, as you wish. It's to your liking. You can choose them however you want. So if health is low and distance to enemy is close, then we should probably execute a script called flee, putting in quotation marks here, right? This is called a rule, and in our case, it's rule 1. Also, I'm introducing a fancy term here. This part of this table is called the antecedent. And this here is the consequent. Now, these tables you will find quite frequently if you read about fuzzy logic, reasoning, inference. Again, we have to understand every row in such. Let me just have another row here then. So we have rule 2, if health is low and distance is near, then, I don't know, execute a script called wait. So by looking at or listening at how I wrote down this row, we can already see. This part of the table is supposed to represent the if part, the antecedent of a clause, and this part is the consequent, the then part, right? Everything here is if, everything there is then. And tacitly we do assume that there is an and between every sort of column element in every row.
Near, right? It should be low and near, right?
Yeah.
Close and near are different.
Yes. Yeah. Oh yeah. Okay. I'll draw it in a second. I don't know. It's like here is distance. This is I don't know close. This is near, and this is far. And again, why triangles and trapezoids? I don't care. I really don't. My job is to expose you to these concepts, not to how you do it in practice. Nobody knows. This is very sad, but nobody knows. Like, wouldn't it be better to define this as close, or this, or something like who knows? I don't. Right? And this is very unfortunate. Very unfortunate. But in these lectures we have to cover lots of ground rather than dig into the depth of it and understand. So we have to learn about these techniques and ideas, and not so much about how to really do it in practice. This is what we're doing in the projects. Right? Now, we have 2 rules, and once again, everything sort of on the left-hand side of these tables is supposed to be the antecedent. That is, if health is low and distance is near, then execute a script called wait. Right? And I don't know, we have another one here, let's call it R4. So here we have if health is medium, and distance is, what do we have, close, then we could attack. I left down rule 3, but you see, I mean, you can do that. And of course, we already see that the more variables we have, the larger these tables become, right? Because then there will be more columns, and the more columns there are, then the more we have, the combinatorics explodes. Like, so basically, the more columns there are, the more rows there will be as well. If you use that, you have to make sure that you basically cover every case. Can that be automated? Yeah, there's lots of research going on these things here. Right? So, yes, people probably do that. I don't know. What I wanted to talk about is the following. Introduce 2 more terms. So let us assume we have, I don't know, designed behavior based on these 2 attributes, health and distance to enemy only. And we have measured them for the current game state, and we have observed a value for h and a value for d distance. We collect that into a vector I shall just call x. Right? If we had more attributes that would be influencing our behavior program, then we'd have larger vectors here, but whatever. So I define that to be x, and now with this x and the rules I have just erased, we can define the following idea. So mu for rule 1 of x is the vector where in each of the elements of this vector we now evaluate, sort of fuzzify the membership of the observed variable. So this is the vector consisting of mu low with respect to h of h and mu close with respect to the linguistic variable d of d. And to make this explicit, let's also look at what it means to write mu of R2 of x. This is the vector where we have mu with respect to low h, and here we had mu near with respect to distance of the, and so on and so forth. Right? Now what I'm trying to do here is to convince you that, at least for the left part of the table I just erased, we can understand every row in this left part of the table as a vector of numbers, right? Because this low is exactly like this membership of something we have measured. This is sort of the membership to low, this is the membership to close, membership to low, membership to near. We can translate these rows in this table into vectors. And now, this was an example. Now the notation becomes a bit cluttered, but do not despair. Given this example, you can understand them. So let us assume, this time in more generality, that we have a measurement vector. So that is, these vectors x indeed contain the crisp values we have measured from within the game world. And we have measured x1, x2, all the way to some xn. So more than 2 measures, not just health and distance to enemy, but I don't know, like, you know, something we have measured. So given such an observation, or a feature vector, or however you want to call it, something that contains numbers we have measured from within the game world, which we now have to sort of map to the fuzzy concept. We have this, we say that a rule R, that is one of the rows in this table, is firing if we have that the membership function of the linguistic term with respect to measurement I and rule R, and the variable with respect to I and R. So this is basically the low or medium thing. Right? This indicates just the terms, low, medium, high, whatever. But we have different terms for the different variables probably. And we also have to indicate what rule we are talking about. These indicate the linguistic variables, so health, distance, armament, whatever. Right? So this is it looks ugly, but what can we do? So this is a way of writing down these membership functions in general. If each membership function in one row of such a table is larger than 0 for all the columns of that row, then we say this rule is firing. Right? We had like lots of rows in the tables, each row was a different rule. All the rules that evaluate to something larger than 0 are set to fire. Right? And we also say that its degree of acceptance is alpha r, so we again indicate the rule we are talking about, and it's supposed to be the minimum, which is just as we convinced ourselves the operation and of all these evaluations of the membership functions in that row r xi r of xi. Okay, so this now really answers our question. We have found a way of fuzzifying crisp measurements. We saw that we can argue with these fuzzy values, with these membership values. We can AND them, and we can represent clauses, that these if-then clauses in terms of these tables, which we just do. We could write down if-then, if-then, if-then. We have these tables because it's a more compact way of writing it down. We have these tables. We can evaluate every row in such a table, and we can check which ones are currently active and which ones are firing. Right? And for those, we can actually say with which degree they are firing. It's again like just sort of ending all these clauses, and we say the degree of acceptance of a current situation encoded in such a feature vector x corresponds to this value here. Okay, one quick example, then we have to point out a caveat, and then we extend that to fuzzy control, and then we are done. So bear with me. Here is an example. Let's say we have observed a feature vector x containing help and distance values, and let's say, for the sake of the argument, the help is 30 and the distance is 2000. So the beauty here is they can have extremely different values, right? That is quite often a challenge if we do a pattern recognition or machine learning or statistical inference with feature vectors, because say if we were to compute gradients on these vectors and whatever, then values with very large instance here probably would dominate gradients. We have to be careful, typically normalize the data. If we use fuzzy reasoning, we don't have to normalize, because we can, somebody has to do it, nobody cares why and how they do it, 25, 50, 100. I simplify this example a bit. This is our fuzzy concept of what it means to be of certain health states. So low looks like this, medium looks like this, and high looks like this. So this is what I'm just making these up as I go. Basically, we have the same for this linguistic variable distance, but with totally different numbers along the x-axis. Say 2,500, say 5,000, and here is probably even 10,000. I don't know in what unit that is measured, but say the graphics engine or the physics engine of the game measures distances between game characters in some unit whatsoever. These would be typical units we'd find there. Then we could say, so this was low, medium, high. Now we would say this is close. I'm making those up. This is near, and this is far. Right. Beautiful. And we had, so this is our classification, and one rule could basically look like this. So we have this is a graphical representation of a rule. Namely, it could say that, I don't know, for D we have this low and close. That is one of the rules we had in our table. We're just making up some numbers. This is really like if you don't have to worry about getting the details of these things. 25, and here I'm using 500. So one of the rules in our table stated that if health is low and distance is close, right? And health is low is expressed by this function, and distance is close is expressed by that function. And now we have observed 30, which is probably like here, 30, and 2000, which is probably like here. These are two values we have currently observed. We fuzzify them, that is, we compute their membership, and we find that 30 has like this membership, and this is bad now. There's supposed to be a height difference here, which is difficult to see. Let me redraw this. These things I should do with slides, like all the graphics. Like so, maybe. Because on the slides, it's not my horrible, drawing that could see that more clearly. So we have fuzzified the h value of 30, and that gives us, I don't know, some number, say 0.4, and this one gives us 0.5, and of course the minimum of these two would be alpha r is 0.4. Right? Just minimize that. Now, what do we do if several rules in such a table are firing? Yeah, that is a good idea. That is, given what we have discussed so far, is the best idea. Indeed, this will happen, right? If we fuzzify these things, we have seen that a height can be tall or very tall, or a health can be low or medium. So usually several rules in such a table will fire. And then we have to ask, okay, so now every rule has a consequent. So far it executed the script. Like now, if several rules are firing, which script should we execute? And she suggested the one with the highest acceptance value. And that's probably a good idea. Right? And this is such a good idea that I don't even write it down. It's sort of the obvious one. And there is another thing we can do, and this is what this was usually or originally developed for. And to understand that, we have to probably take yet another step back. These scripts we have been talking about so far have never been made precise, right? I said there are states, and to every state in a finite state machine there is a script attached, and then if we are in a state we execute that script, and now we said we don't even need to have states, we just check like what script should be executed, and how to devise these scripts, right? What, yeah, how to do it. This is beyond what we'll do in the lecture, but think about this. If you were to attack an opponent, so you would have a script for the NPC that would realize an attack. That attack could be really fierce or rather reluctant. Right? If the NPC has a low health value, it's probably more important to flee than to attack. So whatever attacking action would be called for in the current game situation might be not as fierce as if the game character is of full health and can really like battle to the death. And what I'm trying to point out is that we can think about these scripts being parameterized. Right? If we have something that realizes attacking behavior, that can be either like very aggressive, so the character would, I don't know, hit with the sword quite a lot of times, or it could be rather reluctant, like I hit, and then probably take a step back, stuff like that. We can parameterize these scripts, and let's not dive into how that can be done, but it can be done. And if we agree that we can parameterize scripts, then we can ask how to choose these parameters. So let's think about parameterized scripts. What do I choose? Let's say parameter aggressiveness. Aggressiveness. We can then think about rules such as, or sets of rules such as health, the distance to enemy, and aggressiveness. We could say this is low, this is close. If it is low and close, then we shouldn't be so aggressive. So aggressiveness should also be low, because if our health is low and we are close to an enemy, it's better to flee, so we shouldn't be so aggressive, right? So this could be rule 1. I don't know, I'm just making up some rules here. If our, let's say, a rule 4 could be health is medium, some fuzzy concept of medium, and the enemy is close, then aggressive parameter could be medium as well. Right? And now here is the situation where linguistic terms occur repeatedly, but this is with respect to health, and this is with respect to aggressiveness. Right? I didn't think of another way of naming these. But we can use what we have done so far to not trigger a script, but to sort of set the parameter of a script. Right? This basically we exchange what we are doing in the consequence. We have parameters here. This is great. I mean, this is immediately obvious. But now we have the opposite problem. We are dealing with this fuzzy variable, and we need to turn it into a number. Right? Of course, we can implement these scripts such that they take fuzzy inputs, but maybe we have to turn them into numbers, in particular if you use, I don't know, machine learning and have to produce vectors here, whatever. How could we turn these fuzzy things into numbers? Let me give you an example that has nothing to do with computer games, but that makes it clear. Say there was a climate control system in this room here, right? And it would measure the temperature and, I don't know, say humidity in the room. So 2 variables, and they can be low, medium, high, I don't care. Hot, whatever, cold, whatever linguistic terms you want to have. And the action could be to either turn it up or turn it down, right? Up, down, large step upward, low step down, like, you know, some sort of value that would indicate how you have to turn the handle or the control. And if we were to realize such a temperature control system for this room here, then of course we could say, okay, it's hot and very humid, so we have to crank up the climate control system. And in order for the apparatus that actually does that, we have to turn that into a number. There has to be some I don't know, electrical impulse that either creates it to the air control system to you know, really make it freezing cold or whatever. So we have to turn these into numbers typically. How do we turn these fuzzy values back into numbers? Now, ever so briefly, this is not really so important. I'm just drawing a picture and leave it at that. You don't even have to take notes, whatever. This picture is a bit confusing, but let's see what we can do. Yeah. So, say we have observed something 30 and what was it, 2000, and we have a rule 1 and a rule 4. and the rule 1 was combining this low thing and this close rule, whatever, and it would tell us that the aggressiveness, so this is h distance, and here we have aggressiveness, in this case was supposed to be low, and I define it like so, and I even drop all the numbers because why shouldn't I, and then, so this was low, distance, wrong one here, make it close, distance is close, and aggressiveness is low, and here we have another rule which says that if the health is medium and the distance is close, then the aggressiveness was supposed to be medium. And now we have measured certain values, so say 30, 30 and 30, and then where was it, 2000 and 2000. And again, my picture might actually be bad. So we have fuzzified this health value of 30, get a membership value. We defuzzify this one, I'll just draw it here. Now if we look for the minimum, this one is has the lower minimum value, the lower membership value, right? And here we have, which one do I have here? I don't know. Trying to turn this one into the lower membership value now. So, like so. So this one is lower. How do we use this information to infer something about the aggressiveness parameter? There are many different possibilities, and this is actually somehow an active area of research. I don't know, it was an active area of research, maybe they figured it out right now. One idea is to basically clip, in this case this trapezoid, at the height of the minimum in our antecedent, and to clip, in this case this triangle here, at the height of the minimum, right? And now we are dealing with a situation where these two rules, basically for the aggressiveness, so A here, we have something that would say low aggressiveness and something that would say medium aggressiveness, and we have clipped these two. So say this one was clipped here, and this one was clipped here. So in a sense, this is just to say that we combine these two responses into something like this, right? And then we simply compute, now this is a shape, a figure in 2D, a polygon, and we compute the center of mass of this polygon, and that's probably, it will be here, right, because this is somewhat a larger area than this one, so probably this is, if we were to have a thread here, then that would balance out if we would put it up here. And to use the x value of this center of mass as the crisp output value of our fuzzy controller. So once again, fuzzy control is typically used like this. You measure something crisp, health, distance within the game world. You fuzzify that using these membership functions. Then you have a rule base. So the process is you have measurement, and you fuzzify, then you have this inference that is doing these all these AND operations here and inferring what comes out of this and maybe combining them into, like, you know, these combined answers of all the firing rules. And once you have inferred this fuzzy answer, you have to defuzzify your answer. Defuzzify. That would be compute, for instance, the center of gravity of this shape, and just take the x value, and this gives us a precise number, and that is the defuzzified number, and that would be the parameter for the script we use to, I don't know, realize the fighting action. Yeah, so I only did that for the sake of completeness. Basically, we should have stopped at where you say we have several firing rules. We just execute the script that corresponds to the rule with the highest degree of acceptance. Right? There we could have stopped. That is okay enough for a game AI. If you want to take it a step further, now you know how to measure something crisp, fuzzify it, do some inference, defuzzify it, and get something crisp out of it again. That's all for today. Are there any questions? Great, then see you next Monday.